All right, so here we go. So on the target check. So first of all, number one, rotating versus revolving. Everybody good? Rotating means it's spinning in place. Revolving means it's physically moving and changing locations. Cool? Cool. All right, number two, describing the forces. I was looking for 5 things. A, pushes or pulls. B, inward. And then name the force. Tell me if the force is friction or normal force or gravity or tension or Roy or what. Good? I tried to make corrections on those. Like if you made a mistake, I tried to, in my crappy handwriting, write down what your mistake was. Is everybody okay with 1 and 2? Do I need to say anything about any of those? Okay, so number 3. This is the one that I want to talk about. I'm looking for a really deep level of understanding here, and I think I did not do a good job front-loading this and making sure you guys understood what the answer to that was. On the homework, it has the answer key, and it says, I swear I put it on there, but I'm pretty sure it says, I don't remember if it's about a bug on a record or a car going around a corner or something, but it says in, what's that? It's a bug on the record. In the homework? Okay, so it's almost the exact same thing. But on the answer key, it says in big, bold letters, I think, if I remember right, it says don't use the word overcome. Okay? Do you guys remember talking about the car driving around the corner and the groceries sliding across the seat? Yeah. And remember I used that stupid font that you guys couldn't read, and I wrote in giant, big, multicolored letters? I think that was a sour, right? Yeah. And I wrote, there's nothing pulling the groceries outward. Right? Why do the groceries go outward? Because we made our seats basically frictionless, so there was nothing pulling them inward, so they went in a straight line, right? But there's nothing pulling them outward. The reason they go in a straight line is because we didn't have any force pulling them inward. Clear? All right. So number 2 is similar, except there's some friction. Unfortunately, not enough. So what do we mean when we say not enough? So here's the deal. Look. So here's our ladybug. Here's our record. Okay? So if I put the ladybug on the record, if I spin it slowly, then everything's good, right? Notice he's, relative to the record, he's not moving. Relative to my hand, he is moving. What's preventing him from sliding off of the record, you guys? Static friction. There is enough static friction to prevent him from sliding off the record, right? Now as I spin it faster and faster, does spinning it faster change the force of static friction? No. But what it does do is it changes the amount of static friction that I need. Right? So if I spin it faster and faster, eventually there's a point where the amount of static friction that I needed to prevent him to slide off just wasn't there. There isn't enough friction to make him accelerate at the same rate as this little X that he's sitting on. Does that make sense? Yeah. And so he slides off. Not because there's anything pulling him off, but because there isn't enough force to keep him going around with the same acceleration as the record. Does that make sense? Yeah. So in other words, the amount of force that we need is bigger than the amount of force that we have. Okay? So there are 2 equations here. Centripetal force is mv squared over r, right? So what this represents is the amount of centripetal force that you would need to make an object with mass m move at a velocity of v around a circle with radius r. In other words, if I put the duck on the x and I spin the record, then to keep him on this x, the amount of force that I would need would equal the mass of the ladybug times the velocity at which that x is moving, squared, divided by this radius. Good? So that's how much force I would need to keep the duck on the x, or the ladybug on the x. Make sense? That represents how much force I have available. It's like how much money I've got in my wallet, right? So I've got this much to spend, but I'm trying to buy a thing that costs this much. Follow? So the problem arises if this is bigger than this. That's when we have a problem, right? Because what we have is less than what we need. Does that make sense? LaShawn?
How's that a problem?
So, it's a problem because that's when the duck or the ant or the ladybug or the coin or whatever the thing is, that's when it begins to slide. Is that what you were asking or no?
Yeah.
All right. Can I make a quick analogy, you guys? It's not actually super quick, but it's sort of quick. But I think so does everybody understand the car driving into a brick wall problem? When you drive your car into a brick wall, you're screwed because the force of the brick wall stops the car, but your body wants to keep moving, yes? All right, so let's dig a little deeper on that same example. All right, so let's do this. So imagine that you have been charged with bringing donuts to some meeting before school, right? So here's the passenger seat of your car. Oops, let's draw it flat so that there's... All right, so here's the passenger seat of your car, and you just went up to Donut Express to buy some donuts, and you put the box of donuts on the passenger seat, and you weren't thinking ahead, so you didn't buckle them in, which you should totally do, you guys. Seriously? I can't believe you guys would overlook that. Buckle them in. Safety first. All right? So anyway, so you're driving, right? And you look down the road, and you see that there's a stop sign. Do you wait until you get a foot from the stop sign and then jam on the brakes? No, because then the donuts are going to keep moving, the car stops, and the donuts keep moving, right? You're going to anticipate the stop sign, and you're going to stop a little ways ahead, right? Follow? So look, guys, listen, please. So look, suppose the donuts have a mass of, I don't know, say 5 kilograms, all right? All right, well, that means that gravity is pulling them down with a force of 49 newtons, right? The seat is holding them up with a normal force, also 49 newtons. Now, if you gradually slow down, somebody see if you can name, what is the name of the force that stops the donuts? If you gradually slow down, what do you got, Joey?
Static friction.
Very good, static friction, right? If you stop quickly, the donuts will slide off the seat. We don't want that to happen, so we stop gradually, using static friction to prevent them from sliding, so our static friction holds the donuts on the seat, right? Okay, so let's suppose maybe the coefficient of static friction between the seats and the donuts is 0.4. Okay, well that means that our maximum force of static friction is 0.4 times 49 gives you 19.6 newtons. Cool? Does that make sense? So that's the most force that I can possibly exert on those donuts to stop them unless I buckle them in or stop them with my hand. Good? All right, squirrel runs in front of the road. I jam on the brakes. Because I jammed on the brake, the acceleration of the car is -5 meters per second squared. I just made that number up. All right, like, shit, squirrel. Oh, shoot, squirrel. Just reported that, so belated earmuffs. So you jam on the brakes, right? The car goes and stops very quickly, right? Now, in order for the donuts to not slide off of the seat, what does the acceleration of the donuts have to be? The same as the car, right? So what we want here is we need the acceleration of the donuts to be -5 meters a second squared, right? Oh, well that means that we need the net force on the donuts to be, well, mass times acceleration, right? 5 kilograms, 5 meters a second squared, and you get -25 newtons, right? So what's the problem? We only have 19 newtons. Right? So what are the donuts going to do? They're going to slide. We do not have enough. We need 25 newtons worth of static friction to slow the donuts down, but we've only got 19 newtons. So they are going to keep moving, right? because there's not enough force to give them the same acceleration as the car. Make sense? This is the exact same thing, except instead of the car stopping, the car is turning, or the record is turning. Make sense? Does this help? Problems? Okay, so to answer this correctly, you need to be talking about how much force you need and how much force you have. Or how much acceleration you're trying to create and how much force you've got to do it. Make sense? Okay. One other quick thing. A couple people used the word centrifugal force. Holy beans, no. No, there is no centrifugal force pulling the duck out. If you wrote that the centrifugal force overcomes the centripetal force, or if you wrote that the force of the duck overcomes the friction, or if you wrote anything overcomes friction, that's not right, because there's nothing pushing the duck outward. Just like here, there's nothing pushing the donuts forward. All right? Questions, you guys? All right, so that is the why the ant doesn't slide off the record problem. It's the why the car doesn't skid off the road problem. It's the why the Russian dude doesn't slide off of the spinning merry-go-round problem. Except, how's the merry-go-round problem different? What does a merry-go-round have that a record doesn't? Handles, right? For you to hang on to or wrap your legs around, as was in the video. All right, are we good? Hey, Brandon. Thank you. Okay, so everybody's good? All right, so that is that. Nope, that's not what I want to do.